Now, I will discuss consolidated drain triaxial test. After proper encasing of the sample in the triaxial cell, the required lateral pressure is applied. Now, drainage valve is kept open. On application of the lateral load, the excess hydrostatic pressure start to dissipate slowly, thereby causing a volume change. Now, shearing is started, keeping the rate of loading as slow as possible. The drainage valve is kept open such that excess hydrostatic pressure can be dissipated and the volume change taking place is recorded. So, here it is the result for consolidated drain test. So, here the shear stress versus normal stress relation, and this is the Mohr circle, and in case of consolidated drain test, and this is the failure envelope. You can see here in case of consolidated drain test, you can measure what should be the cohesion value, that is effective cohesion, and you can also measure that what will be the effective angle of shearing resistance, that is pi dash. So, from the consolidated drain test, you can measure the C dash and phi dash, which are the effective stress parameter. Now, the main reason for keeping the rate of loading slow is to prevent the development of excess pore water pressure, and this test is continue until failure takes place. I will just show you some specimen calculation for triaxial shear test. So, this is the specimen calculation for triaxial shear test. So, first that mode of testing. Mode of testing, that is unconsolidated undrained, unconsolidated undrained test. Now, you know the diameter of the specimen. Diameter of the specimen is equal to 3.8 centimeter, and next initial length of the sample is 7.6 centimeter. Next, initial area, that is A0 is equal to pi by 4 into let us say d square, if d is the diameter of the specimen, if this is d. So, you can write pi by 4 into 3.8 this is centimeter, this square, you can have 11.3 centimeter square or 1.13 into 10 to the power cube, this is millimeter square. So, you can determine that what will be the initial area. You should know what should be the dye density. You can calculate the dye density, you know how to calculate dye density. Dye density is equal to 1.546 gram per cc. You know how to calculate that specific gravity. We have already covered this. This is 2.72 and you know void ratio, and void ratio that is designated at E is equal to 0.97 and the degree of saturation, degree of saturation that designated at SR is equal to 92.54 this percentage. So, you know this all this data, what will be the diameter of the sample, what will be the area of the sample, what will be the dye density, specific gravity, etc. So, these tests are to be performed under the different loading. So, this is unconsolidated undent test. So, you measure the deformation that is in millimeter. You measure the strain that is in percentage, and then you measure the AC, that is corrected area. AC is the corrected area. Okay. This is millimeter square into 10 to the power cube, and then you are measuring at a different confining pressure. Sigma 3 is equal to, let us say, 50 kilopascal. So, you should know that what will be the load under this confining pressure, that is kilonewton, and what should be the deviator stress. This is sigma d is the deviator stress, that also in kilopascal. So, like this you can also the another confining pressure, that is 100 kilopascal. What should be the load? Kilonewton, load kilonewton, and the sigma d kPa deviator stress, and similarly for another confining pressure is 150 kilopascal. So, you can determine what should be the load, and also you can calculate what will be the sigma d, that means deviator stress, that is kPa. So, under different confining pressure or cell pressure, it may be 50, it may be 100 kilopascal, it may be 150 kilopascal. Let us say that deformation is, this is 0 and strain also 0, and initial area which we calculated earlier, that is 1.13. initial area which we have calculated earlier, and then load is equal to 0, then sigma load here is equal to 1.13, this is 0, this is also 0 in the beginning. I am just showing only for the under the confining pressure of sigma 3 is equal to 50 kilopascal. Similarly, you can also calculate for the sigma 3 is equal to 100 kilopascal as well as sigma 3 is equal to 150 kilopascal. I am just focusing here only for the 50 kilopascal. Okay. You can, let us say, measurement for this deformation is 0.3, just say 0.6, you will have some data. So 0.3, let us say the strain value is 0.394, AC corrected area you can have 1.134 and load is 0.02 and the deviator stress is 17.637. Let us say for a deformation of 0.6, the strain value is 0.789 and corrected area 1.138 and load is 0.03 and the sigma d, that is deviator stress, is 26.362. So I will just focus that how you can calculate this deviator for a particular deformation 0.6, how you are measuring the strain, then corrected area, and for a confining pressure of sigma 3 what will be the load and what will be the deviator stress. So like this you can continue with the different deformation. It may be the 0.9, 1.2, 1.5 and you continue like this deformation, you continue until you can have some maximum value. Okay, is continue like this, any deformation value, it may be 8.7 etc. like continue. So you can have some maximum value. So you will be knowing that what will be the maximum value, that deviator stress maximum value for the 50 kilopascal. So let us say that you are having that maximum value, let us say 200, 290, okay, for a particular deformation of 8.1. Similarly, you can have that what will be the maximum deformation under a confining pressure of 100 kilopascal and what should be the maximum deviator stress for a confining pressure of 150 kilopascal. Now I will show here that for this deformation how you are measuring the strain. So strain can be in terms of the percentage, that is delta L by L0 into 100. So what is delta L? Because your deformation is 0.6. So 0.6 deformation, so 0.6 this divided by, I say the length of the sample, as I told you earlier, that is 7.6 centimeter, or here it will be the 76 millimeter. So this is the length, initial length of the sample, this into 100. So you can have this value is 0.789 percentage. So you are having the strain value of 0.789. So, here you can see for this deformation this strain value is 0.789. Okay. Now, we calculate the corrected area, that is AC. Let us say that corrected area that is designated at AC. AC you know that is A0 divided by 1 minus this is epsilon. Okay, strain. So, what is A0? A0 we have calculated earlier, that is this A0 is 1.13 into 10 to the power 3 millimeter square. So, we can write 1.13 into 10 to the power cube. This divided by 1 minus epsilon. That means, epsilon is equal to, we have already shown you this epsilon value, and that value is this strain here 0.789. So, in percentage it will be the, this is 0.789. So, in percentage it will be the 0.00789. So, if you calculate this, so you can have the corrected area will be about 1.138 into 10 to the power cube, this is millimeter square. So, you are having the corrected area AC is equal to 1.138 10 to the power cube, which I have shown you in this table, that corrected area, that is AC corrected area 10 to the power cube 1.138 into 10 to the power cube. So, you determine that what will be the corrected area. Next, I will show you how to calculate the deviator stress. Okay. So, deviator stress it is designated as sigma of D. This deviator stress is equal to load divided by AC, that is corrected area. So, what is the load? So, when the load is applied 0.03. Okay. So, load is equal to 0.03, this divided by AC, that is the corrected area. So, corrected area we have already calculated and shown in this table 1.138 into 10 to the power cube millimeter square. So, we can write 1.138 this into 10 to the power cube, this is millimeter square, and this into 10 to the power minus 6. We are expressing in terms of kilopascal. Okay. So, we are having the deviator stress. If you calculate, we can have, this is 26.362, this is kilopascal. So, we are having the deviator stress sigma D is equal to 26.362 kilopascal. So, here table we are showing the deviator stress sigma D is equal to 26.362. Like that, for the different deformation, you can calculate that what will be the deviator stress. Okay, that is sigma D. So, at a particular deformation, you can have the maximum value of the deviator stress. Let us say that maximum value is equal to 290 kilopascal, under the confining pressure when sigma 3 is equal to 50 kilopascal. So, we are having that when the confining pressure, let us say that confining pressure is, when the confining pressure, that is sigma 3 is equal to 50 kilopascal, we are having the maximum deviator stress in kilopascal, you are having the maximum deviator stress 290 kilopascal. Okay. Similarly, when the confining pressure is 100 kilopascal, then you can have the deviator stress value. Let us say this deviator stress value is 297.1. So, for the let us say first case, this is the case 1 and this is the case 2, when the confining pressure is 100 kilopascal. So, we find the deviator stress is equal to 297.1 kilopascal. Similarly, for the confining pressure when sigma 3 is equal to 150 kilopascal, you can have that maximum value of deviator, say let us say 300.1 kilopascal. So, we can write in case 3 that when the confining pressure is equal to 150 kilopascal, so you can have a deviator stress is about 300.1 kilopascal. So, under the different confining pressure, so you can determine that what will be the deviator stress, that means you know that what will be the deviator stress. And you can also draw that deviator stress versus the axial strain curve under different confining pressure. So, how you can draw the curve in between the deviator stress and the axial strain under different confining pressure. Suppose if you draw a line like this is the axial strain, this is axial strain, okay, that is in percentage, and this is the deviator stress, and that is sigma 1 minus sigma 3, we say sigma 1 minus sigma 3, or you can say sigma d, and that is in kilopascal. So, this is under different axial strain, this value may be 2, 4, 6, 8, 10 like this, 12. So, from the table you know what will be the axial strain which is known to you, the axial strain value, and the what will be the deviator stress. So, for a particular strain you can have a deviator stress. Okay. So, you can have a some point like this for a particular the cell pressure or confining pressure when sigma 3 is equal to 50 kilopascal. So, this is the relationship between the axial strain and the deviator stress. So, this is for a particular confining pressure of 50 kilopascal. Similarly, you can have the another curve, it may be like this. Okay. For a confining pressure of sigma 3 is equal to 100 kPa, You can have like this curve for 100 kPa, you can have this curve for the 50 kPa, you can have the another curve maybe like this So, this is for the when the sigma 3 is equal to 150 kPa. So, you can draw this 3 curve under the different confining pressure. So, confining pressure is increasing, the deviator stress also that increasing. So, you find from this test you can draw a correlation between the axial strain and the deviator stress. This is very important parameter in triaxial shear test, how you can determine the deviator stress and the corresponding strain, because you should know what should be the strain is required and corresponding what value you should take into account for the deviator stress. And also equally under you can also express this curve in drawing the Mohr circle diagram, and because you know that what should be the initial that normal stress and what will be the final normal stress. So, you can draw a correlation between the shear stress and the normal stress. So, between the shear stress and the normal stress you can draw a number of the Mohr circle, you can draw the Mohr circle envelope, and also you can determine what should be the shear strain parameter C and phi, and which we will explain in my next lecture. Thank you.